There are several different correlational tests that are used in practice, such as the Spearman correlation for rank data, for ordinal data, or the biserial correlation for nominal data. But the one that we're going to be concerned about in this class, and the one that we'll do together, will be the Pearson product moment correlation, or just for short, the Pearson correlation. The Pearson correlation is the most commonly used correlational test by researchers. Just like any other statistical test that we've learned this semester, it comes with its own set of assumptions. You'll note that of these 5 assumptions, 2 of them are exactly the same as our previous statistical tests. However, the other 3 are different, and so we should talk about those other 3. The first one that we should talk about is that in a Pearson correlation, both of our variables need to be scale variables. In other words, they both need to be either interval or ratio. So that's different than our previous test where we only needed one of them to be scale. Now we need both of our variables that we use for the correlation to be a scale variable. Our participants for our study should be randomly selected from the population of interest. That's not different from any other test. So let's move on to the assumption that populations should be normally distributed. Now the assumption itself is no different, but how we talk about it will be a little bit different. You will remember for the Z, T, and the F test that we could use the central limit theorem to help us with this particular assumption. In other words, if we had 30 or more observations in a group, then we could assume a normal distribution. The problem here is that all of our observations are at the individual level. We're not averaging over individuals to reduce differences among those individuals. And so we can't use our rule of 30 here. We can't use the central limit theorem to help us. So that means we have to remember all the way back to Module 1 when we talked about verifying the normality of variables. So we need to look at the measures of central tendency, the mean and the median. How similar are they to each other? We should also plot a frequency polygon to look to see if our distribution appears to be normally distributed. And then lastly, of course, we learned about the skewness statistic, that we can calculate a statistic to determine whether or not our variables are skewed or if they're normal. Now we would do this for each of our variables in the correlation. So if we're looking at 2 variables, we would do this for each of those 2 variables. If you remember back to Module 1, here is our formula for calculating skewness. We would take the mean of our variable, subtract the median, then divide by the standard deviation, and then take that amount and multiply it by 3, and that would give us a number for skewness. We would then compare that skewness number to our table to determine whether or not we had a normal or a skewed distribution. And again, we would assume that it was normal if the skewness number fell between the lower and the upper bound from our table, given the sample size in our study. Now, I'm not going to ask you to calculate a skewness statistic for the exam. It would take too much time, and it's time that you don't necessarily have, but you should be able to talk about it with the assumption as far as what you should do to determine whether or not your variables in the population are normally distributed. The fourth assumption is that our variables should be linearly related to each other. Now when we say linear, what we're saying is that our observations should be best represented by a straight line. So in our scatter plot, the points in our scatter plot should be best represented by a straight line. If we go back to our example of course grade and absences, we can see that there's a lot of variability among our individual students in the scatter plot. But generally, it appears that as absences increase, course grades tends to decrease. And so if we were to draw a line that best fit these data points, then it should be a straight line. If we were to draw a single line on our graph, we would want to know whether or not that single line would represent a straight line or a curved line. So a curved line would have a mathematical function such as a quadratic equation or a cubic equation, whereas a straight line equation would probably best fit these data points that we have here. An example of a nonlinear relationship might be between 2 variables such as the number of practice trials and the performance in percent at a given task. And so here again, each point on the graph on the scatter plot represents a different observation, But notice that it's not in necessarily a straight line, that a curved line may better fit these data points. If we drew that line in, we would see that it would be best represented by a curved line. In particular, we still see that as practice trials increase, so does the performance in percent, but you'll notice that it's at different rates depending on the number of practice trials. That fewer practice trials results in higher increases in performance than later practice trials. And that tends to be true with most things, most skills that we learn, that the first few times that we practice it, we have greater gains in performance. But after a while, we start to peak, that no matter how many more times we practice, we don't increase our performance by very much. And so that would be a relationship best represented by a nonlinear line or a curved line. Another example of a nonlinear relationship might be between stress and performance. That at some level we need a certain amount of stress to perform, and so up to a certain point, as stress increases, so does performance. But then once we pass that optimal level of stress when it comes to performance, then the more stress we have, the more our performance starts to decline. And so in this case, you have a relationship where it's increasing up to a certain point for performance, and then it starts to decrease after a certain stress level. And so a quadratic line rather than a straight line would best represent these data points. The last assumption that we should talk about is what's called homoscedasticity. Now, you don't need to be able to say that word or be able to spell that word. All we're really talking about is equal variance. That the variances should be the same across our levels of our variables. That for each variable of x and y, the variability as we increase across the values of those variables should be the same. If we return back to our example of absences and course grades, you'll note that for every level of absences, for every increase in absences, there is a certain number of students who has a recorded course grade. Well, the variability, or the differences among those students, should be the same at every level of absences. So in other words, for every number of absences, the variability or spread of course grade should be the same. And that's what equal variance is, or homoscedasticity. So if we were to look at students who had 2 absences, we could create a normal distribution that represented all those students in their course grades when there were 2 absences. We could also do the same thing for students at 4 absences and 6 absences and 8 absences and so on and so forth. And the spread of those course grades for each one of those levels of absences should be the same. If they were approximately the same, then I could draw 2 lines that represents the upper and the lower bounds of each of those normal distributions. And if we had equal variances or we had homoscedasticity, then most of the observations should fall between those 2 straight lines. And so you can see here that there's quite a few of the observations that fall outside of those 2 lines as the number of absences increase. So this might be an example of a violation of equal variances, that it appears that as absences increases, so does the variability at each level of absences. Or in other words, the more spread out course grades tends to be as absences increase. If we put 2 dashed red lines that represents the actual variability at each level of absences, you can see that those 2 lines tend to get farther and farther apart as we increase in absences. And so in this case, again, we would technically use a statistical test to find out if we have homoscedasticity or not. We won't do that in this class, but we can eyeball it and we can see that the variability in our responses tends to funnel out or get wider as we increase in the number of absences. So this may make us think that we're not meeting our homoscedasticity or equal variance assumption. Those are the 5 assumptions for a Pearson correlation test. When we come back to class, we'll talk about a couple of those assumptions and what we'll say when it comes to an exam, such as whether or not we have linear relationship or if we have equal variance. But in class, what we'll do is we'll go through a correlation from start to finish. So thank you for taking the time to watch the video, and I'll see you in class.